Good afternoon, and thank you for joining us and welcome to the Stantec Water webinar series. It's our pleasure to introduce Elise DuBois as our presenter today. She will discuss tank terminology, functionality, and modeling times, as well as share with us the critical data needed to optimize your tanks and systems. I am Tony Fink, your hostess for today. During this meeting, you will be in listen-only mode. We invite you to submit questions at any time during the presentation. If you're joining via computer or your mobile device, you can do so by selecting the Q&A icon in the top panel of your screen. Your questions will be addressed following the presentation. We will also be dropping in messages to the audience in that same Q&A panel. And with that, Elise, I will pass it over to you to get us started.
Great. I'm just going to turn my camera off here before we get going. And thank you very much, Tony, for the introduction. So here's today's agenda. At the end of the day, you will be able to determine the size, shape, and material of your tank or tanks, have a better checklist of how to operate your tank, be able to talk with technical staff about various appurtenances, understand the importance with regard to how your tank functions and what that means for your water quality. There are 8 basic tank shapes, which we will discuss in more detail. Elevated tanks, a general term that describes the blue tanks in the picture, is a term that is still used as a general classification. But the term we hear a lot that is vague and means nothing is ground storage. All tanks shown here are considered ground storage. So toss that term out. As we move through the presentation, terms with an exclamation point triangle are important, and on this slide, terms next to the yellow line, although important terminology, are discussed later when we get to those sections. I'll point out any terms you need to be aware of as we go. So materials, they fall into 2 basic categories. Concrete, typically we see types 2, 3, and 4. Type 1 is pretty rare. If you have an odd-shaped tank, it's a type 4 concrete, as they are usually designed by an engineer, not a tank manufacturer. There are 2 main steel classifications within AWWA, welded and bolted. I've listed some specialized materials into the categories they fit in. Normally, steel tanks are plain plate steel, nothing fancy. I should note that stainless tanks are very rare, very expensive, and not typically found in the municipal market. However, glass fused to steel tanks are the same plate steel with a glass coating on both sides, and those are very common. Typically, underground tanks are very big or very small sized. They are notorious for issues, mostly as the only access is through the roof. They are almost always a type 4 concrete tank, meaning an engineer designed them and a contractor built them, much like you would have someone build you a pump station. They can be from a tank manufacturer, but it's rare. Underground tanks are always buried by at least 50% of the sidewall height. Nameplate data. This tells you who manufactured or built the tank, the nominal diameter and height or length and width, the year or serial number. These are not found typically on type 4 concrete tanks. If these are not on your tank, which is the ideal location, they should be handy in an office. Maybe you put it as art on the wall. But it is critical to know this information, even 50, 75 years down the road, because we can still contact some of these manufacturers to get critical data on your tank. And that could be used for any number of reasons. For type 4 tanks, you will need a copy of the original shop drawings and/or contract drawings and specifications. Take care when getting your tank recoated and rehabilitated. These data plates should be temporarily removed and replaced. If need be, it's a good time to have a new one made if the etching is worn down from exposure to the elements. Reservoirs are named based on their dimension. If the tank is wider than it is tall, it's a reservoir. Sometimes they don't look like they meet the definition, but check the nameplate data to determine if it's a reservoir or a standpipe. The top tank is indeed, no, I'm sorry, it's the bottom tank is indeed a reservoir. The diameter is only a foot or so more than the height. So that blue tank. Some key terms for you to know. The knuckle, that's the point where the roof meets the shell. It's an odd term, but used a lot. And ladder cage, OSHA requires that these be removed and has since 2011 because they do cause more harm than good. Key term for you here is manway. It's an opening on the shell to access the tank interior. And here the key term is hatch. So this is an opening on the roof to access the tank interior. Essentially, they provide the same function as the manway on the shell, but due to location and slight differences in the appurtenances, they're known by different names. Standpipes, the difference between a reservoir and a standpipe is in the dimensional ratio. Per AWWA, a standpipe is defined that it is taller than it is wide. The bolted steel tank on the left with the glass fused to steel coating is what you're seeing there in that picture. And the other one is a welded steel tank on the right. So that's just a little bit of a difference between them, even though they both qualify as steel standpipes. Geodesic domes, these are typically aluminum, triangular shaped. They're normally found on the glass fused to steel bolted tanks. However, I have seen geodesic domes on concrete tanks. We also have some anchor bolts, nuts, and housings here. Those are typical on all of your reservoirs, standpipes, and you'll even see them on the elevated tanks from time to time. So your key term here is a cable clamp. These keep your cables tidy. They help to prevent galvanic or dissimilar metal corrosion. And a sample box, which we're going to talk about a little bit more on the next slide. So why do you need a sample box? They're multi-level. They let you sample the water in the tank. And there should be one for every single tank out there. They're typically installed as a 3-level high, mid, and low sample port, but on tanks with less than 50 feet of wall height, we will install only a 2-level, which would be a high and a low sample port. So why do we do this? And this is kind of critical because pulling samples off the inlet-outlet piping or at nearby facilities do not provide you with the water quality in the tank and will frequently provide better water quality results than you actually have. So this leads to a false sense of what's really happening in your tank. And what does that mean? Well, if you pulled a sample off your inlet outlet, which is pretty typical, and your residual was 0.4 parts per million, and you were aiming for a residual of 0.4 parts per million, you think the tank has a residual of 0.4 parts per million. But if you sample from within the tank at the same time at the various levels, you might find that the top of the tank has a residual of 0 parts per million, and the bottom of the tank has a residual of 0.2 parts per million. So just like pulling a sample using proper procedures is important, where you pull the sample from is also important. Spheroids are defined by their shape. They go by different names for each manufacturer, and some of the more common names and manufacturers are shown below. When in doubt, if you tell technical staff you have a tank that looks like a golf ball on a tee, we all know what you're talking about. And here, a term for you is the bowl, and the bowl on the tank is defined as the area between the top of the pedestal and the top of the overflow. So it's not quite the full height of the tank, but it's pretty close, and it's that black arrowed area you can see there. And that's typical on all the elevated tanks. Some more key terms for you. Blowers, these are used as part of an aeration system to remove total trihalomethanes. Vents, the old school name is a finial vent. You'll still hear that used to describe any type of vent out there, but the pressure vacuum vent is the modern vent that's better for your tank. The vent cannot be your overflow. We see that a lot on concrete tanks. They are two separate things and need to be kept separate. And all vents require two screens, a bird screen and an insect screen. Ellipsoidal tanks are defined by the multiple legs holding it up. The shape of the bowl varies a bit based on the size, hence all the different names. This is an older style of tank. It's really been replaced by the spheroid style for the smaller tanks and by the composites for the larger, but this is still made by the manufacturers listed. Composite tanks are the only tank that has both steel and concrete materials. However, the bowl is steel, which is why all elevated tanks fall into the steel category. So the pedestals are the only part that's concrete. A fluted column tank, these are the same as the composite tank. The difference comes down to that column. This one's corrugated, and like the stripes, the ribs run vertically, whereas on the composite, the lines or the panels, whatever you want to call them, are horizontal. It's an easy way to tell the difference. These are all steel. Composite is multi-material. So custom tanks, these are fun, my personal favorite. A custom tank typically doesn't fit in the standard shape, but sometimes, like in the case of a teapot, it fits a typical shape but has extra metal to make it custom. I do happen to know that on the teapot, the handle is the overflow pipe. So it has some functionality, but for the most part, they're just fancy tanks. So now that you've got a basic handle on the basic shapes and terminology, let's take a look at how the tanks work. We all know how tanks work from a plan or piping perspective, but what's really going on with them on the inside and in terms of functionality? So these are the goals of every tank. Equalization water is the water in the tank to help meet peak demands. These are times when your pumps or plant will be supplying the distribution system, but the tank is also supplying water to the system. Equalization water just evens out those flows in times of peak demand where your pumps may not be able to keep up. In terms of water quality, this is what we strive for to produce the best water quality. So what's really going on? In the past, we've thought of tanks as being glorified pipes. They're like a soup can in your pantry. It's there when you need it, otherwise, it's forgotten. Some will tell you a tank works just like a reservoir. They stratify, have varying water quality seasonally. But the reality is that it's both and neither of these and a combination of some of the elements of these, which is probably the most confusing thing you'll hear today. So what's really happening in that tank? Well, let's take a closer look. First, we have stratification. So we know that the coldest water is on the bottom of the tank and the warmest is on the top. But did you know that a shell heats up, the tank stratifies from the outside to the inside too? Keeping the tank's internal water temperature within 1 degree Fahrenheit or zero 0.8 degrees Celsius between the uppermost level of water and the lowermost is the industry standard for good water. Warmer water helps bacteria to flourish and disinfection residuals to decline fast. Biofilms, just like in the distribution system, biofilms gather on tank walls and floor, and they're hard to remove. They can lead to bacterial outbreaks and poor water quality. Sedimentation, this needs to be cleaned when it hits 2 inches or every 5 years, whichever is more frequent. Sedimentation is organics. Organics help to burn through your disinfection residual. Stagnation. Stagnation is pockets where the water just doesn't move. This sample tank doesn't have a mixer, so there's a lot of stagnation. But let's look at mixing and modeling and how that might help these problems. On the left are a couple of the more common submersible mixers. On the right, a CFD model. We'll look at these a bit in this section to explain how they correlate and why they are so important. So this is a typical Type 4 reservoir, not very big in size, from an actual client's project. The next few slides are going to look at how we modeled the tank and came up with a resolution to the problems shown. So in this particular tank, there are 35 columns and one staircase. Anything in your tank that impedes the flow of water will create problems with water velocity. This CFD model looked at the water's velocity and how it is moving after 2 hours. For the most part, we're finding the water really doesn't change after 2 hours. It's going to be as mixed or unmixed as it gets, with no discernible differences after that time. So let's skip ahead a slide and follow the water through this tank. So without mixers, the water that comes into the tank, which is up here at the inlet, takes a very long time to reach the outlet. The outlet will get fresh water into the system only in the first day or two. This client did not want mixers, but this figure helped them to understand that they were going to have big problems. And this figure tells us to meet our goals, mixers are required. So let's look at that water path. The water comes in really strong on these nice black arrows, kind of follows this green pattern. Some of the water comes over here, hits that staircase, hits the corner, and fizzles and dies. Following this guy, it comes down and around, goes back up, picks up a little momentum as it comes around the inlet, hits all these columns, and slowly peters out until it hits the wall and just stagnates there. It doesn't do anything. And then when the outlet is active, you get a little bit of pull from this corner to the outlet, but otherwise there's no movement in this tank. So what affects how the water moves in your tank? First and foremost, location and number of inlets and outlets. A combined inlet-outlet is worse than a separate inlet and outlet pipe. However, the location of those pipes is critical. From the physical modeling book, which is down at the bottom there, which looks at all sorts of combinations of inlet and outlet piping along with insertion points into the tank, such as through wall, through floor, above waterline. We know that the best option to provide some mixing is if the inlet and outlet are separate pipes and if both pipes come through the floor and are located 180 degrees apart. We also know that without mixers, there are a few cases where the tanks actually mix. So what's best for mixers? Mixing systems are required based on turnover times and temperature or stratification differentials. Turnover time is a calculation. It's typically done with SCADA data that looks at all the inflows and outflows of your tank and determines the actual amount of time for the tank to completely drain and fill once on an average over the course of several years. Turnover time is related to water age, but is different from water age. Good turnover times are 3 days or less. Really good turnover times are multiple times per day or once per day. Typical turnover times that we see are 8 days or more. So let's look at active versus passive mixers. 20 years ago, mixers were new to tanks. We were just starting to see them, and the only options available were passive mixers. These are now primarily used in clear wells or tanks that turn over multiple times per day. Active systems, these come in a variety of types, as you can see in the chart. This is the current standard for mixers in most tanks, and I should note that some states or provinces have regulations that require all new tanks and tank rehabilitation projects add an active mixer. Some just say mixer, and some do not have an opinion. Regardless of the regulations, a mixer will not harm your tank. It will most likely help to improve water quality. Aerators are used in conjunction with mixers, but are not mixers. So what's the purpose of an aeration system? They are used to reduce total trihalomethanes. If your total trihalomethanes are not high enough, in other words, greater than 60 parts per billion, we can't remove them efficiently. Aeration, bubbles, these are really kind of confusing terminology for people. Bubbles, like the picture on the left, come out of a bubble mixer, large or small, and the bubbles float from the bottom of the tank to the top, getting larger in size as they go up. Aerators, like the sprinkler pictured, spray the water into the airspace above the waterline. A blower on the roof then forces new outside air in, while the tank vent allows the TTHM saturated air to exit the tank. And velocity, which is the biggest fear I hear from clients, is that if I put in a mixer, my tank will swirl like a whirlpool or a tornado. In reality, the water stays pretty calm with minor movement, similar to a swimming pool when no one's in it. Something I hear a lot is that a recirculation system or a baffle systems are mixing systems. They are not, plain and simple. So baffles are used to create contact time. That's their primary function. They force the tank to operate in plug flow if done right, but they provide a lot more surface area. They don't add any energy to the system, which is what causes mixing. Recirculation systems just keep the water moving, but not mixing, which can really be confusing. Think of these like a train on a circular track. The train only moves in circles, never up, down, sideways. It's only in the path designated. Recirculation systems do the same thing with water. They move the water through a pipe in a continual loop. So back to our problem tank from earlier. How did we know mixers would work? Well, we installed 3 in the model, let it run for about 4 days to produce a 2-hour graph that you're seeing here. Before, we had very little water movement, and it was only at the top edge of the tank by the inlet. With the mixers, we're now seeing a lot of water movement around the mixers, and then it spreads out. So are there still pockets of water that don't move well? Yes, it happens. It's more prevalent in non-circular tanks and tanks with objects that impede the water flow, columns, stairs, etc. But this is typical of what we like to see in a tank that will be well mixed. Could we add a 4th mixer? Yes. But when we add too many mixers, the mixers cancel each other out. Or in other words, the water from the first mixer hits the water from the second mixer, and that water just stops, creating a dead spot or stagnation zone. So this is a similar model run for a standpipe. Here we're looking at multiple levels within the tank, from the floor in the second row to the top water line in the bottom row. And we're looking at 3 different scenarios. The initial conditions on the left are when nothing is happening in the tank, no mixers, no inflow. Case 4, which is the second column in, is with a specific mixer set, and in this case it was the Gridbee GS12 sheet flow mixer and a pair of them. We can see by the top row that these mixers mix well at the bottom of the tank. There's a lot of velocity, but it peters out as the water moves up the tank. Case 5, which is that third column in, looks at small bubble mixer, and case 6, the far right and the solution we proposed, is 2 small bubble air mixers. So why air? We use air when the tank has a height around 100 feet or taller. The air just moves that water up the tank better. Okay, so to circle back to our sample tank, we've made some changes, as you can see in black. We have a mixer in the sample tank. This is making things homogeneous and reducing the stratification to within 1 degree Fahrenheit or 0.8 degrees Celsius between the top and the bottom of the tank. We've added temperature sensors at the high and low level. This keeps us appraised of stratification and helps to ensure the mixer is doing its job. Because the mixer is making things homogeneous, we tend to see less biofilm growth. The water's always moving, which doesn't allow that bacteria to stick. We've added some sampling ports at the low and high levels in the tank so we can monitor the actual water quality. Do we still have some sedimentation and stagnation? Yes, but it's normally reduced. And we would have determined the type of mixer to be used, active as it's powered and on 24/7, 365, and run a CFD model to determine the number of mixers. We don't need to run a model for every mixer installation, but for odd-shaped tanks, tanks with problems, or tanks that have dimensions that are extreme, so for example, a 200-foot high but 25-foot diameter tank, we would run the model. Realize that most states, provinces now require that an engineer design the mixing system in your tank because they will need to sign off on permit applications or the drawings. Ever wonder how we size a tank or what goes into it? Are there rules around it? Let's take a closer look. There's more involved than what you would think. So tank sizing, it applies to all the shapes. Some considerations. Tanks are really a balancing game. We look at them from a hydraulic standpoint and a physical characteristics standpoint, and we really try to balance the tank so that it not only suits the community's needs today, but the needs in the immediate future and long-term future, while providing the best water quality we can with the technology and tools available. The hydraulic considerations should be looked at every 20 to 40 years during the tank's life. So why is size so important? This is really a Goldilocks situation. If we oversize a new tank for future use and the future use doesn't occur, water quality problems can occur, hydraulic problems, and others. Too little, you may not be able to provide the flow required for your community to grow. We need the tank to be just right, not too big, not too small. If your tank is more than 50 years old and you are getting ready for a rehab, ask your tank engineer to look at the size. This is critical if you're having any water quality issues. But it's good to know if you've outgrown your tank or if your tank is oversized. Sometimes it's a better solution to replace the tank and get the right size and the right hydraulics than it is to rehabilitate the tank. So this is what we look for to get that tank just right. A couple of new terms for you on the right side of the slide. Dead water, it's an odd term, I know, but it's water that cannot be used because it doesn't meet the hydraulic grade line. So this figure shows what all the different water uses are in your tank. We really want that dead water to be less than 10% of the volume. This may mean changing the style of your tank. So now we've gotten up to speed on terminology. We've talked about what's happening inside the tank, what water quality issues happen in tanks, a remedy to fix the water quality, and how to make sure we have the right amount of storage and what shape that storage should be in. So let's talk about caring for your tank. So this final section of the presentation is the how-to of making your tank function better. Some would call this operations and maintenance, but I think optimization sums it up nicely. So up to now, we've talked about the structure, how to minimize problems within the structure, but how do you keep that structure in tip-top condition? Maintenance. Most operators check their tank once a week, sometimes less. This should be a daily stop, even with all that high-tech SCADA, the alarms and sensors. When you get there, walk around. Fun things like graffiti are more often than not found away from where you come in. If you walk around your tank and you have a foundation or a floor issue, you may find soggy ground when it didn't rain. You might never see that otherwise. So once you've been keeping up with that everyday walkabout to check things out, there's still more to do, but on a less frequent time frame. So when mowing or plowing, do that away from the tank. Don't send stuff into it, send it away. Power wash the exterior yearly. It does make a difference and will prolong the life of your coatings. Most coating systems for tanks are currently expected to last for 20 to 25 years. Some will go as long as 30 years, depending on the location and care. The manufacturers require that you maintain these coatings, and a nice wash makes everything look shiny and new. So our last maintenance tips, inspections. Please don't skimp on these. ROV inspections, or remote operated vehicle, by inspection experts are critical. Your tank engineer will know who to call if you don't. An important takeaway is that a sanitary survey, although it may tell you of deficiencies, is not the same as nor as detailed as a complete tank inspection. This replaces the more costly diver option. However, depending on the shape of your tank, getting it clean to remove those sediment beds may require a diver or an ROV. Divers can clean all the shapes. ROVs and divers can clean and inspect your tank with the tank online. And failure to keep up with those inspections and cleanings will require the tank to be taken offline, and usually for costly reasons. So hopefully you now understand the tanks in your system a bit better, from being able to identify some of the key parts to understanding what's happening inside. Who would have thought that there was that much going on inside a tank? But if you have mixers that are lagging or need mixers, don't go it alone. If you're looking at a rehab to your tank, let your tank bestie help. That's what they're there for. From helping you to get a thorough and complete inspection report to determining if your tank is still working for you. And remember, although tanks are frequently known as the soup cans of the pantry, they need love, and they are so much more important to your system. Any questions?
Well, thanks, Elise. We appreciate you sharing your expertise. We actually do already have a number of great questions here already, and I encourage our listeners to keep those questions coming by using the Q&A dropdown located at the top of your screen. All right, so our first one is, can the tanks in my system be retrofitted with sample stations if they are not a standpipe or a reservoir tank?
Yes, they can. We can retrofit them. It may be a little bit of a tank downtime. You may need to take the tank offline, or it will need to be done with a diver, but it can be done.
All right. All right. Question number 2. When talking about sizing in the hydraulic considerations, you omitted emergency. Why is that something that's not being considered?
Let's go back to that slide. Yeah. Okay. So we don't go with emergency storage because your fire flow is your emergency storage. If your tank was designed correctly and calculated correctly from a hydraulic standpoint, everyone's looking at a minimum of 24 hours of storage, which is typically your average day demand. When we look at these, we look at a couple of things. First, we look at your average day plus your fire flow to see what that number is. We look at your average day plus equalization, which is essentially 20% of your max day demand. And we look at your max day demand as the third number. We compare these volumes that come out of the calculation. And when we do that, we determine what the right size is. And that may be the midpoint, whatever. But the term emergency, which is kind of funny because the only emergency that we have is either having a day's worth of storage, which is what the EPA here in the US recommends, or you're having a fire, which is the other emergency. Those are both already accounted for. So if there's emergency storage, and I use the finger quotes on that one, that's required, that's above and beyond that, it should be spelled out in the regulations as 48 hours of storage, 72 hours of storage, or 2 times the fire flow recommendation.
All right. Well, how about this next one? Are blowers required for mitigation of THMs for potable water tanks? I haven't seen this used previously.
Yes, they are. When you do an aeration system, which is a typical mitigation for THMs, we do put in a blower. Most of them are on the roof of the tank, so you don't really notice them unless you happen to have that bird's eye view. Otherwise, we can do a ground level if your tank is short enough and put the blower there, but it is required.
All right. This was on an earlier slide as well. The pockets of stagnation seem random. Is that normal?
Yes, very normal. That's the sample tank. Let's see if we can get back there. Here it is. So on the sample tank here, I showed them kind of randomly here, there, and everywhere. And that's because it really is. The water in a tank, even in a circular tank, doesn't swirl well like that tornado picture, right? In a nice clean outer edge. It really kind of eddies and flows and ebbs more like a river, kind of randomly inside. And that's why you get these odd dead spots. They just appear randomly. There's no rhyme or reason. There's no, to my knowledge, mathematical formula or string theory type thing going on that says it's going to be here. There's no predictive way. So they're just there. They are what they are.
All right. So you mentioned, why is dead storage emphasized as 10% of the volume or less? Shouldn't it be zero?
I get this one a lot. We have arguments about this one with the structural engineers frequently. Let's go back to that slide for a second. Okay, I'm not going to find that slide easily, so we'll skip it for now. But essentially, we emphasize it as 10% because the most expensive thing you can do is use water to hold up water. So if you have a standpipe and you should have an elevated tank, you've got a lot of dead storage. And depending on the regulations, and here in the US, every state's a little different. In Canada, it's a little bit more streamlined for the provinces. But what ends up happening is we see everything from required PSI of 35% or 35 PSI to required PSI of 20 PSI as minimum threshold elevation service amounts. Most of the states are still at 20 PSI, and the threshold amount is the amount that's serviced at the homeowner's front door. The 20 PSI is at threshold elevation. 30 PSI is what's used for fire flow. So we want to make sure that below that 20 PSI is no more than 10%. In an elevated tank, we should theoretically be able to make it 0% all the time. But that doesn't always happen because the critical elevation in any tank is that overflow elevation that you're seeing. Because of that overflow elevation, being what it is, and especially on the elevateds, having standard head heights on the bowl, which makes them cheaper. That's the difference between the overflow and the bottom of the bowl. We may not be able to get you to 10% or less without adjusting that overflow or costing you a lot of money. So we aim for 10% because we want you to be able to use all the water in your tank or almost all of the water in your tank, but it doesn't always happen. So it's just kind of a standard goal. The 0% is the ideal. It happens in, I would say, probably less than 1% of all the tanks designed out there.
Oh, wow. All right. Well, here's a follow-on. Would strategically placing the mixers in the tank reduce the stagnation, sediment, and biofilm?
Yes, it does. If we place them correctly, if we do a CFD model to ensure that they're really placed correctly, it helps to reduce all of that. People with mixers, or clients with mixers, I should say, tell us all the time that, hey, we've had to order less hypo, or, we're having higher disinfectants than we thought we would get. Like they're exceeding what we normally used to see. And that's part of the reason of having mixers. When you're homogeneous, you're treating the same water quality, meaning your residuals are the same. Everything is very much the same. It's great. We love to see homogeneous tanks. So when we model the mixers, we look at all of that and try to get the best mixing volumes that we can. So you have more active mixing than less. We do know that it doesn't change a lot after 2 to 3 hours in your tank, but over the course of the tank, the water will move through the entire tank. Sorry, over the course of several days, typically about 3, the water does move all the way through the tank.
All right, so I think you answered the second half of this question about the mixers being modeled, but can you give the audience some of the main design factors that you look at when you're looking at the
Yeah,
mixers?
yeah. So when we look at them, first we start off with if you need active or passive. And the only time we really use passive is if you have a clear well or your tank is already showing by the calculations that you're turning over, multiple times per day. So most tanks fall into that active. When we start looking at it from there, then we look first at sheet flow mixers because they're what I like to call the plug and play systems. You can drop them in while your tank is running. They're pretty straightforward. They run 7 to 10 years, and then you ditch it and you get a new one. There's no real anything to fix or replace. After that, we look at your tank height. If you're over 100 feet, we're going to skip past those sheet flow mixers because we know they're not going to work. If you're around 80 to 90 feet of tank height, we're going to definitely consider them, but we're also going to look at the bubble mixers. We use the bubble mixers when you have tall tanks. When all else fails, we like a good bubble mixer because they're kind of almost always working. And there are 2 types of those. There's small bubble mixer, which looks exactly like some of those plug and play sheet flows. It's more or less the same unit, slightly different innards, and they use generators. So you're adding another component to take care of, which is why we try not to go to a bubble mixer unless we have to, because the more you have to take care of, the more time consuming it is. And those use a generator to blow air, no big deal. After that, we really look at some of the other mixers out there. They're less frequent, less in use. I've heard people ask me to look at draft tubes, not understanding that a draft tube or the pipe and valve system, those are really passive mixers. They So if you don't meet the requirements for a passive mixer, we're not going to look at those. They were the standard. The draft tubes were the standard, 20 years ago. They're still kind of the primary standard for elevated tanks. We still do put active mixers in elevated tanks. You're not stuck with it. We also when we look at mixers, we really like to look at what's going on with your water quality. Are we just needing to mix the water? Or do you have THM issues? Do you have other disinfectant byproduct issues? Do you have a biofilm issue? Because sometimes that will relay what else we're looking at. If you have a biofilm issue, we're going to tell you clean your tank, and then we're going to say, but your biofilms are originating from your source. So we need to figure out what's going on at the source, because we can clean your tank, we can scrub it down really good, but those biofilms are just going to come back. Does that help, Tony?
I think that answers it.
Okay.
Next question. So, when space or budget is limited,
Yeah.
is a flow meter a must for an in-ground reservoir? I understand a flow meter is normally seen on both inlet and outlet pipes of an elevated tank. How common is it to see a flow meter for an in-ground reservoir?
They're actually not very common. We can do other instrumentation. We don't normally check the flow going into and out of your tank. We're getting that based on your hydraulic model, based on what else is going on. So when we put in flow meters, because it's a client requirement, it's a regulatory requirement, we don't necessarily need to do the more expensive one. There are some other places that they can be done in your system, depending how your system's laid out, but it's not a typical requirement that I've seen.
All right, next question in. I think it kind of follows your last question you answered. Is an altitude valve a must for the inlet or the outlet of an elevated tank? Would it run well without it?
So we can run your tank off of SCADA and off of radar level instrumentations. It still requires a motorized valve, or you need separate inlet outlets with check valves. But if your tank isn't set up to float on the system, you need some way to shut down that inlet side of things. So in that case, we like either the altitude valve or a motorized valve. And the altitude valve can be a simple PRV with some solenoids on it. It doesn't have to be the full altitude valve, depending on what's being controlled by what the setup is, and what kind of space you have, and the amount of money to be spent.
All right, I really like this one. I read your blog. Why do you refer to tanks as the soup can of the pantry?
Because to me they really are. So when I think about tanks and I think about all the good stuff going on inside them that we've looked at, that stagnation and the plaid look and everything else when they're not well taken care of. And by that I don't mean to diss an operator at all. It's truly what we don't know because we're just learning about these things in the last few years. So, everyone that I talked to over the years, as long as I've been working in the tank industry, which is about 20 years now, um, a lot of people are like, yeah, no, it's the first thing everyone blames is their tank when there's a problem. And the last place anyone wants to fix anything is in their tank, right? Would they drive by them? I mean, how many times do you drive down the highway going to the next town over or on vacation, and you probably pass hundreds of tanks and you don't ever recognize they're there. Um, we don't hear a lot about them. They're kind of the unsung heroes of the water distribution system. They're there, they do their job. And much like that soup can in your pantry, you really don't think about it, right? Yeah, I don't even pay attention to what's in my pantry as far as soup goes, unless it's the winter and I really want soup, or I'm not feeling well and I really need soup. So I kind of think of them because they resemble at least the standpipes, the soup cans, as a soup can in the pantry. It's always there, but it's always forgotten. It's something that if you open your pantry today, when you get home, you'll go, oh yeah, look at that, we have soup. Um, but can you remember when you bought that can? I don't.
All right, I've got two more sitting here, so I'm going to put out
Okay.
a last call for folks to put their questions in now. What do you look for in a good inspection report? What makes it complete?
Oh, these are fun. So first, we want something that looks at the structural. We want it to look at the steel. We want it to look at the concrete. We really want it to tell us what's going on with the actual physical structure, not even looking at appurtenances, just the steel or the concrete. That's the first thing. The next thing, we want to know what these experts' idea is to replace them. We want them to look at the coatings. We want them to test coatings. If you don't know when your tank was last rehabbed, or if your tank is dates back to the 1900s, which is an odd thought now, but if your tank originated in the 1900s, we need to test the coatings. If your last rehab was more than 25 years ago, we need to test the coatings. And that's because we're looking for lead, we're looking for chromium in the coatings themselves, which was very, very common and did not stop when lead paint stopped in homes. So, something to remember, you might still have lead paint because you haven't rehabbed your tank since the 1900s. Um, Besides that, we like to look at the appurtenances. We want to know what's going on with them. We want a ton of pictures. The more pictures we get, the better. We like to look at it from a code standpoint. We want to see what kind of ladder do you have on there? Does it meet the OSHA requirements? Does it have the right heights? Does it have the right gap, especially on the standpipes and the reservoirs between the ground surface and the spot where you can actually start the ladder, where your ladder door is? We want to see that. So there's a lot of things we like to see. And what we get a lot of reports of is here's a half a page that says from engineer, somebody who used to be in the coatings industry or in the, tank rehab industry. And it says, yep, your tank looks good. It should be good for another 5 years. And then you flip through it and you get 20 pages pictures, and the pictures don't show you anything. So we like the more information you can give your tank bestie, the better. There are some companies out there that do really good inspection reports and some that don't do them as well. So, don't be surprised if your tank bestie looks at whatever you normally use and goes, we're happy to do this rehab work for you, but we're going to include an inspection report with an inspection company that's going to give us more detail. And those inspection reports, just for a price range, are relatively inexpensive. Here in the US, we see them around 3,000 to 5,000 for a pretty detailed inspection report.
All right, last one here. Why should we use cable clamps? Why not just run the cable up the side of the ladder? Or why can't we just allow the cell companies to use their own methods?
Oh, good question. Okay, so cable clamps, we like them. We like magnetic cable clamps if you can't get the actual steel ones welded on or bars put into your concrete tank for the same purpose. But the primary reason is that cell companies, especially, like to put on aluminum and other grades of steel. We see stainless, we see carbon steel, we see all sorts of different things that are slightly different than what your tank is constructed of. As a result of that, what ends up happening is, yes, their stuff doesn't rust, but it eats the shell of your tank. So we'd rather have it eat those cable clamps, which is, a good sacrificial chunk of metal that if you have to replace that, that's cheap money to replace one or two of those. But when you have to put patch plates on your tank and pit filler and replace steel on the inside of the tank wall because they welded directly to and damaged your coatings, and then all that sat for another 10 or 15 years, and now they've gone ahead and clamped a whole bunch of stuff directly into the sidewall of your tank. Those dissimilar metals create what's called galvanic corrosion. That galvanic corrosion eats the steel and causes a lot of problems. It's more prevalent on steel tanks than concrete, but we still like to take care of the concrete tanks and not damage that outer layer. And for the life of me, I can't think of the name of the stuff, but it's typical of a Type 2 tank. So it's that shotcrete coating on the exterior. We don't like to damage that because that allows damage to continue to bore in as it weathers over time. And that can in turn damage the steel, the rebar inside your concrete tank. So,
All right, I don't see any other new questions. So with that, we're going to wrap it up today. Thank you to Elise and for all of you for your participation. We've had a lot of great requests for copies of this presentation, so please check in with Elise for more. You can find her contact information and also a link to her blog located in the Q&A panel. You will receive an email shortly with your participation certificate. We will also be posting this presentation on stantec.com if you would like to listen again or share it with a colleague. Our next presentation will be next Wednesday, September 25th. Sandeep Satyamurthy, Stantec's Director of Water Innovation, will be discussing how to balance nutrient removal and energy management, as well as the necessary steps needed to create more sustainable and integrated resource recovery facilities. So we hope to see you again soon. And with that, enjoy the rest of your day.
so what happens is when we do our calculations and on that chart, and so